Welcome to qnawire.
In this problem, we need to solve for the linear and angular velocities of each sphere after the impact. So that's for letter A. And for letter B, the velocity of each sphere after they have started rolling uniformly. So the impact is assumed to be perfectly elastic. So sphere A of mass m and radius r, which is rolling without slipping with velocity v1 and angular velocity omega 1, hits an identical sphere B, which is initially at rest. So this produces an impulse and causes sphere A and sphere B to roll with angular velocity omega A and omega B respectively, and to move with velocity VA and VB respectively. So let's first look into the impact on sphere A. So I have here a sketch of the scenario. So for sphere A, so since according to the problem, sphere A is initially rolling without slipping, so we can say that omega 1 is equal to V1 over R. Now, applying the principle of impulse and momentum and taking the moments about point G, which is the center of the sphere, with the clockwise direction taken as the positive direction, so we'll have, so I omega 1 plus 0 equals, so I omega A. So this, from this we can see that omega 1 is actually equal to omega A. So which is equal to, so this means that omega A is also equal to V1 over R. Now, writing an equation for the linear components of momentum, so for sphere A, we're still on sphere A, so we'll have, so M V1 minus, so the impulse equals M VA. So this is our equation 1. Now, let's look onto the impact on sphere B this time. So I have here a sketch for sphere B. So again, applying the principle of impulse and momentum and writing an equation for the linear components of momentum, so we'll have, so 0 plus, so the impulse p dt equals, so mvb. So this is now our equation 2. Now, adding equations 1 and 2, so the impulse would be cancelled out. So we'll have, so mv1 equals, so mva plus mvb. So the masses would actually cancel out. So this will become, so v1 equals, so va plus vb. So we can have this as our equation 3. Now, writing another equation from the equation for the coefficient of restitution, so we'll have, so the equation for the coefficient of restitution is equal to, so E is equal to negative, so VA minus VB over V1 minus 0. So this can be written as, so E V1 equals VB minus VA. And since E is equal to 1, because the impact is perfectly elastic, so we'll have, so V1 equals VB minus VA. So this is our equation 4. Now, taking the moments about point G, so again the center of the sphere, with clockwise direction taken as positive, so we'll have 0 plus 0 equals, so I omega B. So this gives us omega B is equal to 0. Now, solving for equations 3 and 4 simultaneously, so we'll get let's write that down. Solving for equations 3 and equation 4. So, VA would be cancelled out, so we'll be left with, so VB equals V1. So, solving for VA, so you'll see that VA is equal to 0. So, hence, our answer for letter A is, so the velocity of the sphere is equal to 0. Sphere A is 0, and then its angular velocity is equal to V1 over R in the clockwise direction. And then for sphere B, so its velocity is equal to V1. And then its angular velocity is equal to 0. Sorry, so VB is to the right. And then angular velocity is 0. Now, let's look onto each sphere's motion after the impact. So, for sphere A, since the sphere rolls without slipping, so we'll have VA prime is equal to omega A prime times the radius. So, next, solving for the moments about the instantaneous point of rotation, since it's again rolling without slipping, so we'll have I omega A plus 0 equals I omega A prime plus MVA prime times R. So, given the shape of the sphere, so its moment of inertia is given by 2 over 5 mr squared. So, substituting this and the equation for V A and omega A from part A, so our equation would become, so 2/5 mr squared times the value of omega A, which is V1 over R, so equals 2/5 mr squared omega A squared plus, so mr squared omega A squared. So, simplifying this, we'll have, so 2/5 mr V1 equals 7 over 5 mr squared omega A prime. So, from here, we can get omega A. So, omega A prime is equal to 2 V1 over 7R. And since VA is equal to omega A prime times R, so VA prime is equal to 2V1 over 7. Next, we'll write the same set of equations for sphere B. So, for sphere B. So, again, since it's also rolling without slipping, so VB prime equals omega B prime times R. And then, for the equation for the moments about the instantaneous point of rotation, so we'll have, so MVB times R plus 0 equals I omega B prime plus MVB prime times R. So, substituting the equation for VB prime and I, so we'll have MV1R equals, so 2 over 5 mr squared omega B prime plus m r squared omega b prime. So this will be m v1 r equals 7 over 5 m r squared omega b prime. So from here, we can get omega b prime equals, so 5 v1 over 7r. And then since vb prime is equal to omega b prime times r, so vb prime is equal to 5 v1 over 7. Hence, the answer for letter B is, so VA prime is equal to 2v1 over 7, and then VB prime is equal to 5v1 times v1 over 7.